given data, the data given to us is the following test results of 230 by 600 volt. So the V1 primary voltage of this transformer is 230 volt, V2 secondary volt of this transformer is 600 volt, single phase transformer. The power rating of this transformer is 7.5 kVA. So it's 7.5 kVA. OSI test, the data get from OSI test is the voltage is 230 volt, V is 230 volt, I that is 1.2 ampere, and the power that is 280 watt. But this data refers to LV side, that means low voltage side. And now we'll calculate it for SC test, short circuit test. So the data from short circuit test is LV side is shorted and V is equal to 26 volt, I is 11 ampere, losses is 155 watt, and this data is referred to HV side. See the difference over here. The data given over here that is referred to LV side, and the data given here is referred to HV side. So definitely this example is going to be little bit trickier one. And now we need to find, we will write data to find. What data we need to find? Full load efficiency. Okay. So now the internet was disconnected for short period of time, but now I am back again. It was just internet connectivity issue, but I am back again. So now let's start with the solution. So first of all, we'll write what we need to find. We need to find the efficiency, and now I think you okay, so I am back again. So there was some issue with the internet. Now I am back again. So let's begin the session again. So the voice is clear. Is my voice is clear to everyone? If it is clear, then please say yes in comment section so that we can move further quickly, because we have already taken a much amount of time and we do not want to waste our time. So please say yes quickly so that we can move further. Okay, so thanks for your responses. Now we'll move further with the equation of efficiency, and you must calculate this example with me, because this one is a little bit more trickier than previous one. So please continue it with me. So let's begin. So the equation for efficiency is output divided by output plus copper loss plus iron loss. So the output we need to calculate, so we'll do it very quickly because in previous two examples we have seen this process. So output is kVA into cos 5, right? You should arrange the bike. Output is equal to kVA into cos 5. What is the kVA rating? kVA rating is 7.5 kVA, and cos 5 we need to calculate the efficiency at 0.8 power factor. So 7.5 into 0.8. Who is calculating it with me? Please answer. 7.5 into 0.8 gives us 6. So 6 kilowatt is the load, output. So we know the output, that is 6 kilowatt. Now copper loss and iron loss. But over here, let us check. One of the data is given is referred to the LV side, and one of the data is given to us referred to the HV side. So when this type of conditions with us, first what we should do is this is our iron loss, right? This is clear. But this is our copper loss, but is it at full load? That we need to verify. If it is at full load, then that's fine, but if it is not at full load, we need to find the full load copper losses. So how we can do this thing? And for this, first of all, we need to calculate the full load current. So full load current, that is kVA is equal to V1 I1. So I1 is equal to, what is kVA rating? It's 7.5 kVA, so 7500 VA divided by the primary voltage, that is 230 volt, right? The primary voltage is 230 volt, but the reading we are getting here, this is referred to the HV side, and we want to calculate the current referred to the HV side, and the voltage of HV side is 600 volt. So in this example, the voltage we are going to take is 600 volt, because we want the current of that HV side. And why we want the current on HV side? Because we want to know the copper losses side, and copper losses is this test is did in referred to HV side, and that is why we are referring to HV side. So this is the trick in this example, and this is good one. So 7500 divided by 600 gives us 12.5 amperes. So full load current is I1 is equal to 12.5 ampere, and what the current given to us over here is 11 ampere. So this loss, this is the copper loss, ultimately WC, right? This WC is not full load copper loss, and when we want to use this equation, we need to use full load copper loss as well as full load iron loss, but this is not full load copper loss, and that we come to know using this equation, right? So the full load current is now known to us. So now we need to find first full load copper loss, WC full load. And what is the equation to calculate full load copper loss is? It's the amount of current I and the amount of power. So the ratio of this the amount of current that we need to calculate, the amount of current that we need to calculate the copper loss, and the amount of current which is given to us. So that is 12.5 divided by 11, the square of this gives us this factor, 12.5 divided by 11 whole square, and the copper loss is 155, so it's multiplied by 155. We have seen this equation in our many previous examples, so this equation is not new to us. So now 12.5 divided by 11, that gives us 12.5 divided by 11, that gives us 1.136, so it's 1.14. So 1.14 multiplied by 1.14 gives us 1.299, right? So it's 1.3 almost. So sorry, 1.3 and multiplied by 155, so it's 201.438. So 201.438, so we'll take it as 44 watt. So WC full load copper loss, so this is the amount of full load copper loss that occurs in the transformer, right? So now we have the amount of full load copper loss as well as full load iron loss. Very good, Saurabh, you have got it right. Now place the values. The output is 6 kilowatt divided by 6 plus copper loss is, it's in watt, so if we convert in kilowatt, it's 0.201 plus iron loss is 280 watt, and if we convert it in watt, then it is 0.28. sorry, it's in watt and convert in kilowatt. So 0.201 plus 0.28 plus 6 gives us 6.481. 6 divided by 6.481 gives us 0.9257. So it's 0.926, right? 0.926. And we want to calculate the efficiency in percentage, so we need to multiply it with 100, and when we multiply it with 100 we will get percentage efficiency, and that is 92.6%. So this is how we can calculate the efficiency. So now we know the efficiency, we want to know the percentage regulation. So the equation for percentage regulation is I1 R01 cos phi plus I1 X01 sin phi divided by 0V2. Why 0V2? Because copper loss is corresponding to this secondary side. That is why we are going to take the voltage on secondary side. So now for that we need to calculate everything referred to secondary side. So it's not R01, this will become R02 and this will become X02. So this is a lot different than the previous one, right? Why we have taken this? Because the copper loss we have calculated over here, it's referred to secondary side, and if it is referred to secondary side, then WC is equal to I2 square R02. So the resistance we are going to be able to calculate, that is also going to be referred to secondary side, and that is why we are writing this equation referred to secondary side. Okay, so now let's calculate the R0 using this equation. R02 is equal to WC divided by I2 square. The WC is 155 and I2 square is 11, because at this much of power loss the current is given to us, that is 11 ampere. So 155, 11 into 11 gives us 121. 155 divided by 121 gives us 1.28, right? So it's 1.28 ohm. 1.28 ohm, it's R02. Now we will go for Z02, because from Z02 we will calculate X02. So Z02 is VSC divided by I2, and short circuit voltage it's 26 volt and the I2 is 11. So 26 by 11, and that gives us 26 by 11, 2.36 ohm. So it's a Z02, and then after we'll go for X02, which is equal to under root Z02 square minus R02 square, and that gives us 2.36 square minus 1.28 square. So I will calculate this thing in calculator and directly writing the answer, and that is 1.98 ohm. Why I have not calculated in this? Because it will take a little more time and we are running out of time, that's why. So X02 is 1.98 ohm. So all the quantities that we require is now known to us. So let's place the values. Current is 12.5 multiplied by R02 is 1.28 multiplied by cos 5, that is 0.8, plus 12.5 multiplied by X02 is 1.98 multiplied by sin 5, that will be 0.6, because whenever cos 5 is 0.8, sin 5 is 0.6, and V02 is the voltage referred to HV side, that is 600 Very good work, Saurabh, Kamlesh, Jairaj, Prince. Saurabh, good work. And now let's calculate this thing. 12.5 into 1.28 into 0.8 gives us 12.8. So it's 12.8 multiplied by, sorry, plus 12.5 multiplied by 1.98 multiplied by 0.6 gives us 14.85 divided by 600. So it's 12.8 divided by 600, that gives us 0.046. 0.046, and as it is percentage regulation, so we need to multiply it by 100, and when we do this we will get percentage regulation as 4.6%. So this is how we can calculate the percentage regulation, right? So percentage regulation and the efficiency that we know. So we know the percentage regulation and efficiency. So this is how we can calculate this example, right?